Hello everyone, my name is Nerhos Padamidis, and today I'll be presenting some early results of our work on using large language models for navigating Wikipedia, not just retrieving facts, but simulating human-like browsing behavior. Our motivation for this early work is twofold. First, humans often scroll, skim, backtrack, and click through multiple links when learning. Our goal is to build agents that can assist or enhance this process, not just shortcut it. Secondly, simulating this behavior in silico helps us understand cognitive patterns at scale, could enable us training or aligning LLMs to behave in more human-aligned, interpretable ways. Can also be useful for synthetic data generation, behavior analysis, and agent evaluation. We choose Wikipedia as our domain for two main reasons: scale and structure. But the kind of tasks that dominate most benchmarks, like question answering in Hotpot QA or reading comprehension, aren't really about navigation. These are reasoning tasks. You're given all the relevant information and asked to reason over it. Navigation tasks are different. The agent doesn't have all the information up front. It has to decide what to read, where to go next, and how to reach the goal with limited visibility. That's much closer to how humans actually explore the web. To study this in a controlled setting, we use Wikipedia, a game built on a subset of Wikipedia. In each mission, the agent is given a source and a target page, and it has to navigate using only internal Wikipedia links. There's no search bar, no shortcuts, just link clicking and exploration. This gives us a repeatable, measurable way to study how well agents can navigate and how close their strategies come to human-like browsing behavior. Once we had this set up, we built a custom environment, one that lets LLMs interact with the world using structured, interpretable actions. We start with real Wikipedia pages, which are built in HTML. These pages include a mix of text, images, tables, links, etc., making them hard for LLMs to process directly. So we apply a transformation layer, something we call LLM reader mode. This is the core of our system. The HTML is parsed using tools like Mozilla Readability and HTML to text to produce a clean, linearized version of the content, like what you'd see in a browser's reader view. This transformation removes layout noise but preserves important structures such as headings, links, semantic groupings. The reader mode module also keeps track of what the agent has seen, its current window position, and its past actions. The cleaned up page becomes the agent's state, a snapshot of the text, sections, visible links, and possible actions. The agent then selects an action, and the action is parsed and applied, which is then transformed into a new state that the agent receives. This closed loop is how the agent navigates the web, just like a human would, but entirely in text. This framework is modular and model agnostic. It's the foundation of our experiments, giving us fine-grained control over what the agent sees and how it interacts. Let's move on to some results. This chart shows the success rate on the Wikipedia task. We compare three models: Mistral 7b, GPT 3.5, and GPT-4. We test two prompting strategies: ACT, which goes straight from observation to action, and REACT, which inserts a reasoning step before the action. We also compare unconstrained versus constrained decoding, where the model can only choose valid actions. A few key takeaways. With constrained decoding, Mistral 7b performs surprisingly well, reaching human-level performance with REACT. REACT consistently outperforms ACT across models. Reasoning helps the agent take more efficient and strategic actions. The performance gap between GPT 3.5 and GPT-4 is clear, but the effect of reasoning is often just as important as model size. Next, this bar breaks down the kinds of actions each agent took using REACT. Notice Mistral REACT with constrained decoding shows a more balanced strategy. It scrolls, jumps to actions and clicks links. GPT 3.5 and GPT 4, on the other hand, mostly just click. They don't explore as much or scroll, and GPT 3.5 shows much more errors. This tells us that constrained decoding and reasoning steps not only improve success rate, but also shape more interpretable, realistic behavior. Moving on to the future work. First, we want to test a wider range of models, especially those with stronger reasoning capabilities. We're also interested in experimenting with more sophisticated prompting frameworks or architectures that better model deliberation and planning. Another direction is to develop new reward models, tailored specifically for navigation tasks. Instead of just rewarding correct endpoints, we want to design objectives that favor human-like strategies, like thoughtful scrolling, backtracking, or exploration. Through deep user studies, we also plan to study how humans actually navigate. Do they scroll a lot? Click quickly? Do they revisit pages? These insights will help us better simulate or benchmark against real behavior, something current datasets don't capture well. Ultimately, the goal is to see if we can align LLM agents to follow human strategies. Can models learn to browse like we do? Can we trust them to act helpfully and efficiently in exploratory tasks? These are the questions we want to explore. Thanks everyone for taking the time for me. Thanks a lot.